In this video we're going to make an introduction about complex numbers. So we are going to see its binomial or standard form and how to represent them in the complex plane, and we start watching at the operations. So just to start, a brief descriptions of which number sets we know. We know the natural numbers, the integers, rational and real numbers. So they appear in history because natural numbers, when we need to count, we need to have two hands. We need natural numbers then. Sometimes we can have debt, so instead of having 10 apples, we owe 10 apples, so we have minus 10 apples. Then we also need to divide things, so we can have 1/2 of a pie. So rational numbers contain the fractions and periodic numbers. And finally, also in nature, we have some measures which are not periodic numbers. So for instance, square root of 2 or pi. These numbers, which have an infinite many number of decimal places, but which they are not periodic, are called irrational numbers, and when we join them with the rational numbers we get the real numbers. We can also do this set of numbers as a solution of equations. So if we have this linear equation, we open the context panel, and when we come here we do solve. So x minus 1 has a solution, a natural number, but x plus 2 has a solution, a negative number, so it's an integer number. So if we add some coefficients, we have that the solution is a fraction, so we need the rational numbers. And if we go to a quadratic expression, we need the square root of 2, which is an irrational number, so we need the real numbers. But what about if we want to try to solve x squared plus 1 equal to 0? If we want to solve this equation, so x squared plus 1 equal to 0, we just isolate the minus 1. And in this case, we can see that we need, if we are trying to find a solution in the real set of numbers, we need a number which square is negative. And this does not have a solution in the real numbers. So if we look at what Maple tells us when we try to solve this equation using the context panel, we can see that Maple is telling us that the solution is I plus I and minus I, which is a complex number. So let's see what a complex number is. So one of the definitions of a complex number is that the set of complex numbers is defined to be all the numbers which are a solution of a quadratic equation where the coefficients a, b, and c are real numbers. So any solution of a quadratic equation, a second order equation, is a complex number. So the first exercise is try to find the solution of this equation here. So let's see if we manage to do this. So we have the equation 6x squared minus 43x plus 84 equal to 0. So we are going to use that the solution of a second order equation is minus b plus minus square root of b squared minus 4ac divided by 2a. So if we do this in this case, we get 43 plus minus square root of 43 squared minus 4,684 divided by 2 times 6. We now can do this operation that we need here using Maple. So we need to do 43 to the power 2 minus 4 times 6 times 84. So this is a total of minus 167. So it's 43 plus minus square root of minus 167 divided by 12. So if we look at the square root, we have a negative number inside the square root. So this does mean that this number is not a real number. However, as we have defined the set of complex numbers to contain all the solutions, we can ensure that this is a complex number by definition. Okay? So if we've won, we can have this solution here. We can paste it in here. So if we want to have the solution, we have it here. So what we are going to do to work with complex numbers? An important definition is that we are going to define the number I such that its square is minus 1, or alternatively we are going to define I to be the square root of minus 1. This number I is called the imaginary unit, and even though when we write by hand we use a small I, With Maple, we are going to use a capital I. So the next exercise tells us to try to find the solution of the same equation as before by expressing it as a complex number. So if we come again here, what we are going to do is we are going to split the number minus 167. We're going to express it at minus 1 times 167. So again, now we are going to split the roots, the square roots. So we have this, and now the important thing is that this is the imaginary unit. So what we get is that this is 43 plus minus square root of 167i divided by 12. So this is our complex number. If we do it using Maple, we just copy this expression here. Okay. I'm gonna copy probably this one here. Let's see if it works. Okay, this one. And now again we use the context panel to solve. And what we get is 43 divided by 12 plus minus the imaginary unit I square root of 167 divided by 12. Okay, so this is a complex number and we express them using the imaginary unit. So now you can go to the test and do the first exercise. Now, another definition which is probably more used is that now that we know that all the solutions of second order equation is a complex number, we know that we can also define this set as the numbers of the form a plus bi, where a and b are real numbers and I is the imaginary unit. So any number of this form is going to be a complex number. Just to check what Maple does, we can define the imaginary unit and just compute its square. So we are going to see that the square root is indeed minus 1. Okay, so this is a new definition. A complex number is a number which is of the form a plus bi, a and b real numbers. So an important thing is that once we have this complex number expressed in this way, this is called a binomial or standard form. Okay, also standard form. So a is going to be called the real part, and b without the I, it's the imaginary part. So a and b are real numbers, a is the real part, b is the imaginary part. So let's do this exercise. So we have z equal to, z equal to 3 minus 4i. The real part is going to be 3 and the imaginary part is going to be minus 4. So it's not minus 4i. This is not correct. Both the imaginary part and the real part are real numbers. Okay? If we do it with Maple, 3 minus 4i, we can use the commands re of z, which is 3 and im of z, and you can see that the imaginary part does not contain the I. Okay, so also when we have a complex number, we can expand the context panel, and we can also have the real part, which again is the same. Okay, and we can do this, and we should, here you have the imaginary part, which is the same. Remember that these are levels that we can, this is just 2.5, so this is the imaginary part of 2.5. Okay. The important thing is when our two real complex numbers are going to be the same, when the real part is the same and the imaginary part is the same. So this is easy. And a very important thing is that any complex number can be represented, or it's associated to a point in the plane. So the abscissa, the x-coordinate, is going to be the real part, and the y-coordinate is going to be the imaginary part. That is, if we have a number a plus bi, it's going to be identified with point a, b. So here, if we have a point which is in binomial or standard form like z equal a plus bi, we just plot this. We put the real part, the imaginary part, this is point AB, so this is going to be equivalent to the complex number a plus bi. So let's do this exercise using the point plot command. Plot the complex number -2 plus 5, 5. Okay. So in this case, you could have a look at the help of point plot, but we are going to plot it directly. So here, as you can see, we have a really small point, and now in order to make the plot prettier, we can change the symbol sign to 30 as we are told in the exercise. We can also change the symbol style and the color, and we can also add grid lines. So this would be a nice plot, but this is not useful if we have to change all the properties again. So what we have done is we have implemented a command for you. This is not a standard Maple command, and in order to use it you have to press enter in the 3 lines. So now every time you want to plot a complex number, you just need to put complex plot and the number. But remember that first you have to read this file. So now that you know this, you can go again to the test and try to do this exercise. So now you know what is a complex number, how it's written in binomial or standard form. Let's go to see how we operate with them. So in this case, we know there are 3 different ways of expressing a complex number, but we have started with a binomial form. So in this form, we can add and subtract easily. We can make products and powers, but we will not be able to do roots. So here you have a small summary of addition, subtraction, product, and division. So let's see how we add 2 complex numbers. So given 2 complex numbers, like these ones, in order to add, we just add as if they were, if the I was standard unknown. So it would be A1 plus A2 plus B1I plus B2I, and then we can have common factor and we had the result. And if we take a minus, so this would be this minus this, so we would get a minus in front of A2, a minus in front of B2. So let's do this exercise. We just have 2 complex numbers and we have to add them. So we have Z1, 1 plus 3I, Z2, 2 minus I. So we just go as we have done all life when we have expressions, even with unknowns. So 1 plus 2 plus 3I minus I. So this is a 3 plus 2I. So let's check if we get the same result with Maple. So Z1 is going to be 1 plus 3I. Z2 is going to be 2 minus I. And Z1 plus Z2 is going to be 3 plus 2I. So we operate as if I was an unknown and everything is correct. Okay. So you can again move to the test and do the next exercise. When we add 2 complex numbers, this just some command is the same as if we add the 2 vectors associated to this number using the parallelogram identity. So we have Z1 here, Z2 here, we do the parallelogram identity and we get the addition. But this is not very relevant. So the important thing is how we make the product of 2 complex numbers. So now we have to, instead of adding, we have to make the product. So we are going to operate as we do when we multiply expressions. So Z1 times Z2, we put Z1, Z2, and now we do the product. So A1 times the first one, A2. So A1 times B2I, this one here. B1I times Z2, this one here. And finally B1I times B2I, which is B1, B2I squared. So from here it's the same as we do when we multiply. And now the only relevant thing, or the only important thing is now I squared is the imaginary unit, is -1. So we put a minus in front of here. So we have these 2 terms where we can take out the I. And then we have A1, A2 minus B1, B2. So let's see if we know how to do this in an exercise. So we have Z1 equal to 1 plus 2I. Z2 equal to 4 plus 3I. So let's do the product. So Z1, Z2 is going to be 1 plus 2I, 4 plus 3I. This is going to be 1 times 4 plus 1 times 3I plus 2I times 4 plus 2I times 3I. So we get 4 plus 3i plus 8i plus 6i squared. This is the important thing. Now this is a minus 1 because I is the imaginary unit, so we get 4 minus 6 plus 11i, which is minus 2 plus 11i. Okay, so let's check it. So z1 is 1 plus 2i. You can see that you can use Maple while you study to check everything you do. You don't need the teacher. Sorry. z1 times z2, and we get the result that we got. So again, you can just, I'm gonna just copy this for you, okay, so that you have this in here. This is the result we got. So now that you know how to make products, you can go to the exercise, and we are going to do one just final exercise, which is we have two complex numbers again. We have to plot them in the complex plane and then add and do the product of them. So let's do it first by hand. z1 is going to be minus 2 plus 4i. z2 is going to be 5 minus 7i. Okay, so the first thing is that this is going to be associated to point minus 2, 4, and the second one minus 5, 7. So if we plot this, let me do it again. So it's not easy, but I'm going to try. Well, I'm not going to try very hard. So minus 2, I'm not going to do perfect matching. Minus 2, 4. This is going to be z1. 5 minus 7. So I'm not using, of course, a good scale. So these are our numbers. Remember that we can plug them by just using the complex plot command. Okay, so complex plot of z1, z2. Okay, this is our plot. And now let's do the product. So we have z1 times z2 is minus 2 plus 4i, 5 minus 7i. So it's minus 2 times 5, minus 2 times minus 7i, plus 4i times 5, plus 4i times minus 7i. So we get minus 10 plus 14i plus 20i minus 28i squared. This is the important thing. This is a minus 1, so we get minus 10 plus 28 plus 34i, which is 18 plus 34i. Let's check it. z1 times z2, okay, it's 18 plus 34i, and of course if we add them, which is very easy, it's minus 2 plus 4i plus 5 minus 7i, so it's minus 2 plus 5 minus. If we subtract them, we just need to remember that now it's important to put brackets, minus 5 minus 7i. So we get minus 2 minus 5 plus 4i plus 7i. So it's going to be minus 7 plus 11i. So let's check it. So it's going to be z1 plus z2, 3 minus 3i, and again z1 minus z2 minus 7 plus 11. And finally, let's see how to divide two complex numbers in binomial form. To divide complex numbers in binomial form, we need to introduce the conjugate of a complex number. So what's the definition of the conjugate? The conjugate of a complex number, which is written as a plus bi, is another complex number with the same real part, so a does not change, but with the imaginary part changing sign. So we have to change this sign here. The conjugate of z is represented by z bar, and is z bar equal to a, the real part is the same, minus bi, we change the sign of the imaginary part. So let's do this exercise. So we have z, which is 1 plus 2i. The real part is 1, the imaginary part is 2. We can also compute these two things using the re command and the im command. So we have this number, so which is going to be the conjugate. We let the same real part 1, and we change the sign, minus 2i. This is the conjugate of a complex number. So once you know this definition, you can now move to do the exercise conjugate of a complex number. The important thing of the conjugate is the next proposition, which tells us that if we have a complex number, then if we multiply the number by its conjugate, we get the real part of the number a squared plus the imaginary part of the complex number b to the square. So it's a squared plus b squared, and this is a real number. So when we multiply a number by its conjugate, we get a real number. So let's see how this is proved. So we have z is equal to a plus bi, and its conjugate is a minus bi. So we change the imaginary part, the sign. So when we have z times z bar, we get a plus bi times a minus bi. So now we multiply the first term a by all the second term, so it's a times a plus a times minus bi, and now we move to the second term, bi times a plus bi times minus bi, so we get a squared minus abi plus abi minus bi b squared I squared. So these two terms are the same, and remember that I squared is minus 1, so we get a squared plus b squared. So we have that z and z bar are complex numbers, but when we multiply them, we get a real number. And this is an important property. So let's do again this exercise. So now we are going to do it with a particular case. So we have 1 plus 2i, so its conjugate, it's going to be 1 minus 2i. We change the sign of the imaginary part. So now when we do this, of course, by the proposition, we know that the real part of z is going to be 1. The imaginary part of z is going to be 2, which is b. So I can clear this out a little bit. So this is b. So this is going to be, by the proposition, a squared times plus b squared, which is going to be 5. But let's check it out because it's the first time we do it. So 1 plus 2i, 1 minus 2i, so it's 1 times 1, 1 squared, plus 1 times minus 2i, plus 2i times 1, plus 2i times minus 2i. So what we get is 1 squared minus 2i plus 2i minus 4i squared. So these two cancel out. This is a minus 1, so we get 1 squared plus 4, which is 5, and we get the result we want. If you want to check it with Maple, we define 1 plus 2i, we define its conjugate, and now we proceed to multiply z times z conjugate, and it's 5. Okay. So now that we know that what is a conjugate of a complex number, and that if we multiply a complex number by its conjugate, we get a real number, we can proceed. You can proceed to do this exercise, and then we can proceed to divide two complex numbers. So in order to divide two complex numbers, what we do is multiply and divide by the conjugate of the number in the denominator. So let's see an example. Let's make a little bit of zoom. So imagine that we have to divide 1 plus 2i divided by 3 minus 4i. So the problem is that here in the denominator we have a complex number, and we want to change this complex number by a real number. So how do we do it? By multiplying by its conjugate. So we have 3 minus 4i, its conjugate is 3 plus 4i. But in order to multiply times 3 plus 4i down in the denominator, we need to do the same in the numerator so that we don't change the number that we have. Now, what happens is that in the denominator down, we have 3 minus 4i times its conjugate, so it's the real part, 3 squared, plus here, if we want to do it properly, this should be a minus 4, but it's the same because then we have a square, so it's real part to the power 2 minus 4, which is the imaginary part, the b, to the power 2. Okay, and now on the top we have 1 plus 2i times 3 plus 4i. We proceed by multiplying. 1 times 3 is 3, 1 times 4i is 4i, 2i times 3 is 6i, 2i times 4i is 8i squared, divided by 25. Now we remember that the imaginary unit to the power 2 is minus 1, so we get these two terms, it's 10i, 3 minus 8, so it's minus 5. And then we can split the real part and the imaginary part, so it's minus 5 divided by 25 minus 1 over 5 plus 10 over 25, which is 2 over 5i. If we check it using Maple, Maple directly computes us the result. Okay, so let's do another exercise. So let's now do another division. We have these two complex numbers, which are these two ones. Z1 is 2 minus 5, 5. Z2 is 1 plus 3i. So Z1 over Z2 is going to be 2 minus 5, 5 divided by 1 plus 3i. Here in the denominator we have a complex number and we cannot make the division like this. So we need to convert it to a real number. How do we do it? We multiply by its conjugate. So we do multiply by 1 minus 3i. But when we do it, we have to do the same in the numerator, so because this is going to be a 1. Now here we have that z is equal to 1 plus 3i, a is 1, the real part, b is 3. So we can use that z times its conjugate is a squared plus 3 squared. Okay? It's the real part to the power 2 plus the imaginary part to the power 2. Otherwise, you can check that indeed if you do this, you get the 10 that we expect. And then on the top, we have 2 minus 5, 5, 1 minus 3i. So now we just have to proceed. I'm going to do the first one times the second one. So 2 times 1 minus 2 times 3i. And now the second one, 5 minus 5, 5 times 1 minus 5i times minus 3i divided by 10. So we have 2 minus 6i minus 5, 5 plus 15i squared. Now we can join minus 11i plus 2. Remember that the imaginary unit is minus 1, so minus 15 divided by 10. So we get minus 13 minus 11i divided by 10. So we get minus 13 over 10, this is the real part, minus 11 over 10, this is the imaginary part, times I. So let's check it. So we have Z1, 2 minus 5a, Z2, 1 plus 3 times I. Now we can check that 1 plus 3i times its conjugate is indeed 10. A number times its conjugate, it's the square of the real part plus the square of the imaginary part. And now we can do the division, z1 over z2, and we get the result that we expected. So now that we have done these exercises, you can move to do the division in binomial form. And afterwards, you can try to do these exercises. These are exercises from 1 to 12. And then if you want, you can also do from 13 to 16.